Hello and welcome to this 12th session on symmetry in chemistry, and I'd like to begin this session talking about direct products. So these ultimately are going to be products of irreps. But just thinking about these products, initially we were looking at matrix representations of operations and how a product of symmetry operations was also manifest in the product of matrices. So you can show a symmetry operation in the form of a matrix, multiplying the matrices together. The matrix product also corresponds to the product of the symmetry operations. And we also found that the characters were kind of preserved in this way. So the product of two matrices giving a third matrix which represents the symmetry operations. Likewise, the character of the first symmetry operation multiplied by the character of the second symmetry operation. Ultimately, the product of those characters gives the character of the matrix that represents the product of the symmetry operations. But we're going to go a bit further than this now, and we're going to be looking at products of irreps. But this does introduce a certain problem, and that is that the different irreps can have different dimensions. So if you were thinking about, say, a two-dimensional irrep being multiplied by a three-dimensional irrep, you realise then that you can't just multiply those matrices together. You can't just multiply a 2 by 2 matrix with a 3 by 3 matrix. And it makes you realise then that these irreps, the irrep itself is actually a much more complicated thing than just a matrix, because really it's a collection of matrices, isn't it, that represents the symmetry behaviour in the context of a particular group. But it turns out that we can combine irreps nonetheless, but it's just slightly more involved using the so-called direct product procedure. And one thing we find, curiously, is that if you multiply two identical singly degenerate irreps, you always end up as the product as the fully symmetric irrep, so A or A1 or whatever. Now in actual fact, if you take any irrep and multiply it by itself, you always find the fully symmetric irrep, but if you had, say, a two-dimensional multiplied by the same two-dimensional irrep, it wouldn't be the only product. You'd have A1 and other products. And in fact, the opposite also applies. If you take two different irreps and multiply them together, then the product will not contain the fully symmetric irrep. And for that fully symmetric irrep, it's kind of has a correspondence with the identity operation. So rather like in that way, if you take the fully symmetric irrep and multiply it by some other irrep, the product is just that other irrep, rather like multiplying the identity operation by another operation. So we see that the characters ultimately are preserved, and when we do the direct product, ultimately we're going to multiply all the characters together for all the different operations, and that will form a product for us that will then ultimately be able to reduce. So here's a character table. So I'm going to show you here the direct product of T1 and T2. So T1 and T2 are both triply degenerate irreps, so their dimension is 3. And one thing we'll find is that when you multiply the direct products together, the result has the product of the dimensions. So if you multiply a 3-dimensional irrep by a 3-dimensional irrep, the product is 9-dimensional. And this follows from the fact that we're multiplying the characters together, because of course the dimension of the irrep is the character under the identity operation. So just like symmetry operations combine with other symmetry operations to give a product that's also a symmetry operation in the group, we can say the same thing about the irreps. So the different direct products of different irreps, the result of that will ultimately be irreps in the same group. And so when we multiply T1 by T2, we get a 9-dimensional product, but there's no way that could be a 9-dimensional irrep. We should be able to decompose that using the methods we've seen into other irreps that are members of the group. And so you can see here that T1 times T2 decomposes to these 4 irreps. And so again, you can see that if you add up the dimensionality of the irreps, you can see they're conserved. So A2 singly degenerate, E doubly degenerate, T triply degenerate. So 1 plus 2 plus 3 plus 3, that comes up to 9. And that's what you get by multiplying the dimensions of the T1 and the T2. So you notice that T1 and T2 are different irreps, and so when you multiply them together, you do not get the A1 fully symmetric irrep. Now there's some real motivations for learning how to use direct products, because they can simplify some otherwise absolutely horrendous calculations. For example, if you're looking for energies, interaction energies between orbitals, of course these orbitals are represented by wave functions, and so if you want to know an energy, let's say between two orbital wave functions psi1 and psi2, what actually would have to be done in practice if you wanted to calculate the exact energy would need to be to take the energy which is actually in the form of an operator. So this is a kind of recipe that acts on a wave function. Then you'd have to multiply as well on the left by the other wave function. These then have to be integrated over all space, so it can be a very difficult calculation. But to make life easier, we can remember that, of course, the energy is just a number, and a number, scalar quantity like this, is essentially a fully symmetric quantity. So the energy itself must have the symmetry of the fully symmetric irrep. And so ultimately, what we need is, if we look into symmetry terms, psi1 times the energy operator times psi2 ultimately has to be fully symmetric, because it's got to be invariant under all the operations of the group. And so we need a fully symmetric result of the direct product of the irreps of these three quantities. Now, the energy being a scalar quantity, the operator is a scalar quantity as well. And so in order for all these three quantities to multiply up to give a scalar, a totally symmetric direct product, it follows then that psi1 and psi2 have to have the same irrep. They must be the same symmetry. And again, it's this idea that if you multiply the irrep by itself, it gives the fully symmetric product. But if they're not the same irreps, they don't multiply to give the fully symmetric product. So psi1 and psi2 must involve the same symmetry. So for example, if you just want to know the energy of a particular orbital, then psi1 and psi2 would both be that orbital. And of course, psi1 there, traditionally you would take a complex conjugate of one of the orbital wave functions, and this way the product of the two complex functions ends up being real. Now, what's good about the direct product method is we can say straight away that if psi1 and psi2 are described by different irreps, then the integral simply has to come to zero. And that's because the direct product of those quantities will be something that's not fully symmetric. And so a non-fully symmetric quantity, when integrated over all space, ultimately will cancel to zero. And so you can actually save yourself a lot of time from sweating over an integral only to find weeks later it just comes to exactly zero. You can deduce straight away from a direct product approach. Similar sort of thing we see in spectroscopy. So if there's going to be an electronic transition, let's say, between two states, then ultimately the transition is going to connect two wave functions. And so the operator that we would have in this case is normally the electric dipole vector, because you know that if something's going to be excited by light, electromagnetic radiation, you've got an oscillating electric field and an oscillating magnetic field in the light, and nearly all the time in spectroscopy it's the electric dipole which interacts with the electron. It's a much stronger interaction than the magnetic one. So we tend to look for the electric dipole vector interacting. So you think about that oscillating electric field, that oscillation we can represent as a vector. So it's going up and down, and so we can think of that as being like plus or minus z or something in the form of an oscillation. So in other words, rather than the energy operator transforming as a fully symmetric irrep, the electric dipole transition operator is going to have the symmetry of x, y, or z. It's going to have a Cartesian axis as it's a vector. Now, of course, if you're going to work out the probability of an electronic transition, a probability, again, it's just going to be a number, and just being a number, it's going to be fully symmetric. So again, the initial and final state wave functions and the electric dipole operator, ultimately those three need to combine into something that's fully symmetric. So those three irreps need to multiply together to give the fully symmetric irrep. So what that means in practice is that when you take the two electronic wave functions, so like the initial state and the final state, the product of those two wave functions will have to have the same symmetry as the electric dipole vector, and that way those two identical symmetries can then combine to make the fully symmetric product. And so actually this is how we determine if an electric dipole transition is going to be seen or not. Because obviously if the probability of the transition is 0, clearly it's not going to be a transition that's going to be observed, so certainly not to a first approximation. And so then we can go through this process here, and of course you could even do the same thing. Quite often just considering parity alone can be quite helpful. So if, for example, you had, let's say, an octahedral complex ion, you've got a centre of symmetry in there, and so all the states will have a parity label, G or U. And of course the electric dipole vector here, vectors are odd parity because they have a particular direction, a plus and a minus direction. And so it means then that your electric dipole vector, which will have U parity, means that ultimately your initial state and your final state, they have to have opposite parity. Because if they have the same parity, when you take the product of those two, then you would have G as the result, even parity. And then when that's multiplied by the operator U parity, it would end up giving you a final product which is U, odd parity. And then when that integral is done, it will all come to 0. So we can say straight away that in any electronic transition in a system which has got a centre of symmetry, that's to say the I symmetry element, you can say straight away that the two states that are going to be connected by the electric dipole transition, they have to be opposite parity to each other. And this is something that we observe, and when you look at UV-vis spectroscopy, this is essentially one of the selection rules that drops out. Of course, it's not the only selection rule, so something might be parity allowed, but might be forbidden by some other rule. But that being said, this is a very quick and easy one to apply, so it doesn't take a moment to determine if something's going to be parity forbidden. And if it is parity forbidden, then effectively you don't have to waste any more time on it because it's not going to be an observed transition, or certainly not a strongly observed transition. And actually this quite nicely links up with transition metal complexes, because when we look at octahedral transition metal complexes, the colours of them don't tend to be particularly intense. But if you're looking for extremely intensely coloured complexes, they're often tetrahedral. And this actually very much relates to what we were just talking about, because of course in tetrahedral symmetry there is no centre of symmetry, there's no symmetry element I, which means that parity is just not an issue. Now, if you do have a centre of symmetry, you've got a bit of a problem with these transitions, because of course these transition metals, they've got partially full d subshells. And so the kind of transitions we're looking at, which are in the correct energy range to be absorbing visible light, these are so-called d to d transitions. So you're exciting a d electron from one d orbital to another d orbital, essentially. But you see, d orbitals, all the d orbitals, as we're going to see later on, they've all got even parity, which is to say if you take the d orbital wave function and reflect it through the origin, it comes out looking identical. And that's really because of the way the phases of the wave function are arranged in space. So for example, a p orbital is odd parity. You've got like a positive phase lobe and a negative phase lobe. You reflect that through the centre of symmetry and the phases come out in the opposite sense. But with d orbitals, they come out in the same sense, so they're even parity. So yeah, so these d to d transitions, you've got, in fact, in a sense, it doesn't even matter, does it, that the d orbital is even or odd parity. The fact that the transition simply involves a transition from a like orbital to a like orbital, clearly the product of those two orbitals is going to be even parity. So actually, even if you had like an F to an F transition, for example, the F orbital is odd parity, but when you put two of them together, multiply their symmetries, odd times odd gives even. But anyway, so a D to D or an F to F for that matter, the transitions between states involving those orbitals, ultimately the product of those two symmetries is going to be even. And then when you multiply it by the odd parity electric dipole vector, you get an odd parity product, and that will integrate overall space to give you 0. And so ultimately then, that boils down to the fact that when you have an octahedral complex, all the DD transitions are going to be parity forbidden. Which actually does raise the question, why are they coloured at all? Because, you know, this logic would have it that it isn't coloured whatsoever. But in fact, what we tend to find here is that when a selection rule like this is broken, the transitions often become palely coloured rather than intensely coloured, because they can't use, as it were, the main mechanism to generate the transition or generate the colour, but they need to find some other way of doing it. And in fact, there are other ways that a complex can get around this. So, for example, at room temperature, in solution, obviously all the bonds are vibrating. And so you've got, let's say, 6 ligands around a transition metal ion. Now, those 6 ligand metal bonds will be vibrating. Now, of course, a vibration can be totally symmetrical, so-called breathing mode, where, you know, all the bond lengths lengthen at the same time in phase and contract at the same time in phase. But it's also possible for there to be vibrational modes that are anti-symmetric. So they're not all in phase. And so when it's vibrating in that sense, in that sort of not in phase sense, then what it will do is it will effectively distort the geometry of the complex away from octahedral, and it can distort it into a geometry where there's no centre of symmetry. And so that way it can kind of bend the rules a bit. It can distort the shape, kind of break the symmetry slightly, remove the centre of symmetry, and then the parity selection rule gets kind of broken in that process. And then so you start seeing a little bit of light being absorbed because you've kind of got around that selection rule. But in the case of tetrahedral complexes, in a tetrahedron there is no centre of symmetry, so there is no parity selection rule. So you don't have to rely upon vibrations or some other cunning way of getting around the selection rule. The transition just becomes much more allowed, and so the colour of the complex becomes much more intense. Now, having considered the symmetries of atomic orbitals, we're actually going to go one step further now and looking at how ultimately these atomic orbitals, which were derived for the hydrogen atom, an isolated hydrogen atom, which is to say in just a spherical symmetry, how we describe those orbitals when we get down to lower symmetry, like for example octahedral. And an interesting case here is that when you're looking at the orbitals purely in terms of spherical symmetry, the subshell of the orbital is effectively an irrep in the spherical symmetry. And of course the subshell represents the orbital angular momentum of the electron. So it's interesting this. We have, because of course orbital angular momentum certainly is a conserved quantity. And so that implies then that we have this, you know, invariance where we have these specific irreps describing specific states, and that we can use it as a quantum number because of this conservation of angular momentum. But ultimately, of course, even though the d orbital symmetries, even though we consider the d orbitals to be equivalent to each other in an isolated atom, so in a hydrogen atom, or when we're looking at the Aufbau principle, we consider the d orbitals all together, they do of course split in lower symmetry, for example in an octahedral complex, where we see 2 different energy levels. And I think it's quite an interesting problem to look at it purely from a kind of group theory and symmetry point of view, how exactly you move from one state of affairs to the other. And so the way you do this, again, like we did before, it's all to do with creating a representation and reducing it in octahedral symmetry. And to do this, we're going to have to work out the characters of matrices which transform our orbitals in octahedral symmetry, and then ultimately to reduce this representation. And so what we'll do is we'll stick just to octahedral rotations, because we're going to stick to the octahedral group, as this is the context where we normally work with the orbital labels. And also we're just going to limit ourselves to the rotations of the octahedral group. So when we rotate the orbitals according to the octahedral symmetry operations, we are going to be at liberty to align the axes in the sense which is most convenient to us. And so the way the d orbitals are defined, the angular momentum of the d orbital is defined around an axis of our choice, which we take to be the z-axis. And so I mean, this is most, if you look at those, it's most evident the orbital on the left there clearly has an axis of symmetry. That's our z-axis. And so we're going to align our axis of rotation with the orbital axis. And so that kind of orientation of the axis there, we are allowed to do that because one thing we do know about these matrices is that the characters of the matrix is invariant with respect to the rotation of the axes. So that is something that we're free to choose ourselves. So how are we going to work out the characters then for the d orbitals under the octahedral rotations? And so perhaps one thing just to mention first of all is that if you've got a subshell quantum number L, then this will have degeneracy of 2L plus 1. So there are 2L plus 1 states of equal energy. So in a d orbital, L equals 2. That's the angular momentum quantum number. And so there are 5, that's 2L plus 1 is 5. So there'll be 5 degenerate states, 5 different orbitals that have this, that belong in the d subshell. And they can be labelled, or at least the degeneracy can be differentiated by the m quantum number, which has these 2L plus 1 possible values going from plus L to minus L in integer steps. And so what's quite convenient for us is that if we can fix our axis of rotation for the octahedron onto the quantized axis of the orbital, that makes life much simpler for us. Because when we rotate around this axis in particular, we can describe it in a very simple way just by varying the so-called azimuthal angle. And so when we define these orbitals, we tend to define them in spherical polar coordinates, which is much simpler than x, y, z coordinates. So this is where the coordinates are expressed as r, theta, phi, r being the distance of the electron from the nucleus. Theta is the so-called colatitude. So it's a bit like latitude in if you're looking at geographical coordinates, except it would be latitude where 0 represents the North Pole. So it's called a colatitude because geographers measure latitude where 0 is the equator. But taking 0 from the North Pole. And then the third angle, phi, this is the azimuth. So this is like the longitudinal angle. And so the nice thing about lining up the axis of quantization of the orbital with our axis of rotation of the octahedron is that with those two fixed, both r and theta are going to be unaffected by the rotation. So all we have to actually rotate then is the azimuthal angle. And the best thing about that is that, of course, when you have the atomic orbital in spherical polar coordinates, that's nice because they factorize out. So you have specific functions just for the radial coordinate. Then you have a specific function just for the theta coordinate, and a specific function just for the phi coordinate. And the phi coordinate function is the simplest function. It's just this complex exponential. So by setting up the problem in this way, we simplify it to ourselves because all we're doing is we're just modifying phi in this very simple wave function of phi, and everything else is going to be invariant. So what we've got up on the screen there is showing the matrix of this transformation. So first of all, if you look at the column vector just to the left of the equal sign, this represents the 5d orbitals, and it's just representing them in terms of the azimuthal function, which is the function e to the im phi. So what we've got up there is e to the im phi for the 5 different values of m. So remember, m goes from plus L to minus L. So it goes from plus 2 to minus 2 in integer steps. So at the top we've got e to the 2i phi, and at the bottom we've got e to the minus 2i phi. And of course it goes through 0. And so when m is 0, the whole exponent collapses to 0, and that gives us the e to the 0 in the middle. So curiously, that middle one, that's the only one there that's actually a real function. The others are all complex functions. And so what we need to do is, in our transformation, we're going to rotate the d orbital functions by an angle, an azimuthal angle. And so we're just going to define it here. We're just going to call the angle alpha. So after you do this rotation, so this will be an anti-clockwise rotation, it means then that the azimuthal angle is going to change from theta to theta plus alpha, having rotated it by alpha degrees. And this is what you can see on the right hand side of the equal sign. we've got the same wave functions, except theta has been changed to theta plus alpha. So clearly we have simply rotated the d orbitals by alpha degrees anticlockwise around the axis of quantization. That's what this means. And so what we then have to do is then think, well, what matrix is it that will transform our d orbitals to these modified d orbitals on the right hand side? And you see we've added this angle alpha, but because the alpha is in the exponent, that is the equivalent of multiplying it by e to the power of 2i alpha, in the case of the 2i, the very first orbital. So if you look there at the big matrix on the left hand side, all we've done here is just put elements in the leading diagonal, because there's no sense in which we're mixing these orbitals up. Each orbital, we're just simply adding alpha to the angle, and so we have to multiply it by essentially the same function that we've got in the orbital, except we just replace the phi by the alpha, and that way we just add plus alpha to the phi function. So e to the 2i alpha multiplied by e to the 2i phi is e to the 2i phi plus alpha, and that's where all we've done is add alpha degrees to the phi angle in the first d orbital. Then when it gets to the second d orbital, then we've simply added alpha to phi, and so in this sense it would just be e to the I alpha, multiply that by e to the I phi, and that gives you e to the I alpha plus phi. So you can see how we've just changed the angle there. With the middle orbital, it doesn't really apply, because m is 0, the exponent's just going to stay 0 anyway. So e to the 0 there, that's just multiplying by 1. And then all the way down to the lower ones. So hopefully you can see how that kind of makes sense, creating a matrix which will rotate our d orbitals by an angle alpha around their axis of quantization. Now, of course, the character for this matrix is going to be the trace, the sum of all those terms on the leading diagonal. And so one way of expressing this mathematically is the sum, going from m equals minus 2 to m equals plus 2, of e to the I m alpha. So that's just a neat way of summing up those 5 exponential terms. And so I've said here that this can be written as the character for the rotation by angle alpha is this expression involving signs. And it involves L, but we know L is going to be 2 in this case because it's d orbitals. And this is an expression, this expression involving signs, it's sort of slightly mysterious looking at it. Where on earth did those signs come from? And it's something which is never really explained properly in books, but I've put together a derivation for this, which I'm going to present to you. As it is doable, albeit a bit tricky. Because of course one thing we do know is that these complex exponential functions, they can be written in terms of causes and sines when they're expanded out. So remember, it's cos theta plus I sine theta for e to the I theta, and it's going to be using this kind of approach we can derive this, just coming up now. So deriving this formula for the character, so I'll just zoom through this. So this summation of exponentials, I've written it, you see I've written it here, so I've taken e to the power minus li alpha out, and then I can write the series as a simple series beginning 1 plus. So this is a geometric progression, and it's going to be easiest, I think, to analyse in terms of the contents of the brackets, where it just begins 1 plus. And so this is a classic geometrical sum formula, and this is the formula that you find in a maths book for such a geometrical sum. So where a in the formula is the first term, so it's 1 here because we're just looking at the formula inside the brackets. Then each successive term is multiplied by e to the I alpha. So to apply that again, it's e to the 2i alpha, etc., because these exponents get added when you multiply them. And then the number of terms in the series is 2l plus 1. So these are the number of orbitals that's involved. That's the dimensionality of our matrix. And so what we can do is we sub these terms into the formula. So we get that first expression on the left hand side, 1 minus e to the I alpha, etc. And so again, what we're going to try and do, we're going to factorize this again. And so you see what I'm doing here is I'm taking out e to the I alpha L plus a half. So this is quite cunning, because then you see when you look at what's in the brackets on the numerator, we've got e to the minus I alpha L plus a half. So you see that will multiply by the term outside in the brackets there to give you 1. And then the second term minus e to the I alpha L plus a half. Of course, when you multiply that by the term outside in the brackets, then those two exponents are the same, so they just add up and it gives you the e to the I alpha 2L plus 1 that we want. And then I've done exactly the same thing on the denominator, except this time it's I alpha over 2 that I've taken out. And so you can see how the contents of the brackets, if they're multiplied out, they give you what's on the left hand side. And so why do we bother going to all this trouble? Well, we see if we manipulate it in this way, it's all going to nicely drop out, because we can apply an identity that we've got in the brackets there, because you can see that what we've got in the brackets are the difference between two of these complex exponentials where we've got different powers, different signs in the power, because it follows that e to the minus ix minus e to the plus ix is by definition minus 2i sine x, and this is going to be the origin of our sines. Now see, what's quite nice about this is that it gives us this geometric progression here in terms of sines, but also when you look at what's been taken out, what we took out was e to the I alpha L plus a half on the numerator and e to the I alpha over 2 on the denominator. And of course, when we combine those together, what we're going to see ultimately is that the alpha over, we're going to have alpha over 2 cancelling, and it's just going to leave us with e to the I L alpha. And what's very nice about that is that when we go back to the original formula, when we very first got the geometric progression together, we had taken out of that formula e to the minus Li alpha. And that's great because that simply combines with e to the Li alpha to give e to the 0, which is 1. And so all those exponentials there just cancel, and that just leaves us with this pure sine formula. So there you go, that's the derivation of our sine formula. Now we can apply that sine formula to this reduction of the symmetry. So you see this formula here is going to be for L equals 2 because we're dealing with d orbitals, and it's for the angle of rotation alpha. And so because we're trying to get a representation in octahedral symmetry, and we're just using the rotations in octahedral symmetry, then all we need to do is just consider what the angle alpha is for each of the rotations in octahedral symmetry. And so in the table, in the group theory table I've written there, the character table, rather than writing the normal symmetry elements there, I've just written them in terms of the rotation. So for example, and I've also written the number of operations in the class. So for example, that first column is going to be the identity, which will be rotating by 0 degrees, and there's just one operation. Then the next one we've got here is going to be the 6 C4 rotation operations. So we've got 6 operations where the rotation is 90 degrees. Then after that we've got 3C2, so that's obviously 3 operations where the rotation is 180 degrees. Then we've got 8C3, explaining why where the 120 comes from. And so what we need to do then is we need to go through this process of working out the character in each case. Now one problem we're going to come across is going to be for the identity operation, because in the case of the identity operation the angle is 0, and so we're going to have a bit of a problem because we're going to get 0 on the denominator. So if alpha is 0, then we're going to get sine of 0 on the denominator, which is 0. And obviously having a 0 on a denominator leaves it undefined. But actually there is a bit of a get out here, because of course being the identity, all this really is just the dimension of the matrix. And so since we've got a 5 by 5 matrix, then clearly the identity is going to have character 5. So we can just drop that 5 in there as just the degeneracy of our state, the 5 d orbitals. Okay, so what we can do is we can go through each of those symmetry elements in turn, and we put the angle in brackets there into the formula and we put L equals 2, and as a result of that, all the numbers drop out in the character. So you see here, with L plus a half, that means we're just going to have to take the angle in the table, multiply it by 2.5. So that will give us a very big angle in some cases. But of course, it's just that angle. We might have to subtract 360 or 720 or something from it, but we just convert that into an angle that we can easily do a sine of, then divide it by sine of alpha over 2. And then that gives us the character that goes in the bottom row there. And so once we've got those bottom rows there, ultimately we can reduce it. Now, because we're just looking at the rotations of the octahedron, we haven't got any reflections, we've got no centre of symmetry. And that's why I've dropped the parity label from the table there. And so what we're going to have to do is we're just going to have to add in the parity label manually ourselves. But certainly looking at the shapes of the d orbitals there, the sort of familiar shapes that we use to describe the d orbitals in the hydrogen atom, you can see the way they're all defined to have even parity. Because you see the colour coding on the picture of the orbital there, the colour coding is the phase. So one phase of the d orbital is red and the other phase is blue. And so you can see that if you reflect that through the centre, through the origin, then the phases all come out the same. So they're all, and this is true for all the d orbitals if you look at them. And so all the d orbitals are going to have even parity. And so that means when we go through this process, we're not going to determine the parity label by this process, but it's fairly obvious to us that all these irreps are going to have G parity labels on. And so in fact we can do this by inspection. It's quite a simple case. So that row of numbers there, 5, -1, 1, -1, 1, you can pretty much see by inspection there, that's E plus T2. So just looking across the E rows and the T2 rows, you can see those numbers are summing up to give the representation at the bottom. And then we can add the G parity label on, as we know they're all even parity. So there you go, we have just mathematically derived the fact that the d orbitals split into two symmetries, two symmetry labels, two symmetry types when they're reduced from spherical symmetry, which is how they're defined, into octahedral symmetry. And we can give them specific symmetry labels here, EG and T2G. So this is the origin of the EG and T2G. You may well have seen d orbitals being labelled this way in octahedral complexes. The d orbitals splitting into two energy levels. And now just a little sort of exercise for you is you might try and do the same thing with f orbitals. And so similar sort of thing. L is 3 for the f orbital. It's the next one in the series, SPD. And the L quantum number is going up by 1 each time, so we're up to L equals 3. We can also see, looking at these orbitals, that all of these orbitals are going to be odd parity. And so you can see that, looking at the orbital on the left straight away, you can see that the red lobe at the top would get reflected into the blue lobe at the bottom, and vice versa, by reflecting through a centre of symmetry. So these are odd symmetry, and in fact it follows, doesn't it, that whenever L is an odd number, the angular momentum, the orbital angular momentum quantum number, all those L equals odd orbitals, they're all going to be odd parity. Like the p orbital we saw is odd parity, and that's L equals 1. Of course, the s orbital being fully symmetric, that's even parity, so L equals 0, L equals 2. Those orbitals are all going to be even parity. So for the case of the f orbitals, when we reduce those to octahedral symmetry, we're going to expect the U parity label on all of those. It's the same idea. We've got L equals 3 this time. So we've got 7 orbitals, we can have a 7 by 7 matrix, and we can have L equals 3 in the formula for working out the representation characters. And so because we're reducing it to the same symmetry, octahedral, then the alphas, the angles are all going to be the same. We're going to have the same problem with the identity, but because it's a 7 by 7 matrix, we're just going to have 7 as the character for that. And so we can just work this through in exactly the same way, and then you get a matrix there which ultimately reduces to A2U plus T1U plus T2U. And so you can see there that the total degeneracies all have to add up. So we've got irreps of dimension 1, 3 and 3, and of course they add up to 7. which is the number of f orbitals, just in the same way that with the d orbitals being e(g) and t2g, they were irreps of dimension 2 and 3. Of course, 2 and 3 add up to 5, the number of d orbitals. And so here's what it looks like in the table. So we've got those characters there for the gamma, the reducible representation. These were just the results of putting in these angles into the formula there, the sine formula. And then once we've got all those numbers out, we just reduce them in the standard way, unless you can do it by inspection. Slightly harder one to do by inspection, this one.